All right, let's take a look at our lesson for today. So we're going to look at properties of functions. Let's kind of zero in. The first thing we're going to look at is the difference between an even and odd function. We did talk about this last year. You may or may not remember. There's a couple of different ways that we can test whether a function is even or odd. One of the ways is algebraically. So this portion up here is the algebraic way that we would test whether a function is even or odd. So this is algebraic. And you may remember this test from last year. What do? We plug in, gosh, I can't even write today. Algebraic. What we do is we plug in a negative x everywhere there is an x, and we look at the result. If the result is exactly the same as when we started, then we have an even function. If the result, once we plug in a negative x, is exactly opposite, then we have an odd function. And so that's the algebraic way or technique to determine if you have an even or an odd function. There's also a graphing way to determine that. And so the graphing way is here at the bottom. Okay, so if the function is even, the function is symmetric with respect to the y-axis. So the line of symmetry would be the y-axis. It would be identical looking left and right of the y-axis. That's an even function, looking at it graphically. So this is graphically. And an odd function is symmetric with respect to the origin, which I always found just really weird. So that means if I go from the origin here and I look here, so this point, we'll just pretend it's like, I don't know, 1.5, 2.5 or something here. And so if that point is going to correspond with this point, so this would be like 1, let's just pretend, I'm going to make up numbers just because it's not clean. Let's say that's 1, 2. This one, the corresponding point would be -1, -2. That's what it means by symmetric with respect to the origin, is that those points would correspond. They would be exactly correspond. Does that make sense? I hope that makes sense. That's what it means when it's symmetric with respect to the origin. So that is even and odd. Okay. Let's stay on this side for just a moment. We did talk yesterday about secant lines. If you remember, we talked about secant lines, and the secant line is like it's attached, it's like in 2 spots right here. That's like the secant line. And we have a formula for, it's called average rate of change. Now, hopefully, probably back in Algebra 1, you learned that slope is a rate of change. Have you heard slope talked to about it as a rate of change? Those words, right? So slope is a rate of change. What this formula does is it calculates the average rate of change. The average rate of change is related to the secant line. And we're getting into calculus stuff right here, just as calculus concepts. The average rate of change is related to the secant line. And as you look at it, it's really just slope. It's really just calculating the slope of the secant line, which stands for average rate of change. Okay, so now let's look at some other things. Let's look over here for our increasing and decreasing. So these words are very, what shall I say? They're very mathematical, very specific. We can either be increasing, we can be decreasing, or we can be constant. Those are the choices. Those are the 3 choices: increasing, decreasing, or constant. And this particular graph right here, what I'm going to do is I'm going to show you visually what that is. This is the algebraic way to be able to determine. It's really mathy. It's increasing on the interval for any value of x in the interval when you know, the first x is smaller than the second x, and the first y is smaller than the second y. I mean, that's basically what that math is saying. But visually, what we're looking at, increasing would be like this location from here to here. This would be increasing. It's increasing. Let's just put a little note here, because I'm reading the function from left to right. And as I read the function from left to right, the function is rising. As I'm reading it, I'm starting at the left like you read a book in English, like you read a book. You read from the left to the right. The graph is rising. That means the graph is increasing. There are a couple of places here where the function is decreasing. This is an example from this spot to here, that's decreasing. And from here to here, those are both decreasing locations. Because, so this is decreasing. Because again, as I read the graph from left to right, the graph is falling, it's going down. And this last portion right here, I'll just circle this piece right here where it's just flat. Okay, that is where the function is constant. It is not increasing or decreasing. I mean, that's it. It's constant. It's staying level. It's like a horizontal line would be considered constant. Okay, so how are we doing on increasing, decreasing, and constant? Is everybody okay? Okay. So now let's look at another scenario. Local, these are local extrema, local mins and maxes, and this is all calculus concepts. These are concepts that we use in calculus a lot. We're just talking about the concept itself. So a local maximum, and this is all, you know, again, the wording is very mathy and it can be very confusing to students. So let me kind of explain to you in like an intuitive way. How do we know if we have a local maximum? So this location right here, that's a local maximum. And the actual maximum is the y value. That's the maximum, not the x value. And that's like a little point where students kind of sometimes make a mistake. If I ask you where the local what the local maximum value is, in this case, you would tell me it's 2. You wouldn't tell me it's 1. All right, so what is a local max? It's basically, think about a local max as the top of a mountain. Local extrema, and let's just write this out to the side, local extrema are like hills and valleys. I mean, that's what they are. You can't have a local extrema here at the end, right here, you know, at the end. That's not a local extrema. It has to be part of, like a mountain range, if you will. It's got to be either at the top of a hill or the top of a mountain or at the bottom of a valley. That's what a local extrema is. Absolute extrema is different. Okay, so I'm just talking about local extrema. Local extrema has to occur at the top of a hill or at the bottom of a valley. There needs to, in other words, if I'm standing on top of the hill and I look to the left and I look to the right, I should see points that are below me. Right, that's a local maximum. I should see points that are below me. If I'm in the valley, so here's the example of here's some local minimums. Okay, so my local minimums, those are like at the bottom of a valley. So if I'm standing in the bottom of it and I look to the left and I look to the right, I have points that are above me. I'm actually truly at the bottom of the valley. Does that make sense? I mean, that's really like a, I guess, an intuitive way to understand. Instead of going through all these words, which we can go through all the words, but I've found that it's really kind of confusing to students for the definition. Okay, so that's what a local, and of course the local mins and maxes, we're talking about the y values. Okay, we're talking about the y values. Gosh, I can't even write. All right, that's local extrema. Okay, the last concept over here is absolute extrema. Now, absolute extrema does not have to be at the peak, at the top of the mountain, at the hill or the valley. It doesn't have to be at the top of the hill or the bottom of the valley. An absolute extrema is exactly what it says. It is the very biggest, the absolute largest point or the absolute smallest point. That's what it is. And so how do we tell that? We look at the graph and we look at visually what is the biggest y value on that graph. Okay, so this one right here, this point right here, that is the biggest y value. This would be my absolute max, and of course it's the y value. That would be my absolute max. Okay, it actually also happens to be a local maximum. That's okay. You can be an absolute max and a local max. That's okay. Okay, so that location right there is also a local maximum. Do we see a local minimum on that graph? Does everybody see where a local minimum is? Where would the local minimum be? Do we see any valleys? We do, right? Right here. This would be a local, that's a local minimum. It's not the absolute minimum, it's a local minimum. So when we're determining our absolute minimum, we need to look for the very smallest y value, the very smallest one. And so right here, this would be my absolute minimum. And of course, that's the y value. Okay, how are we doing on the difference between a local minimum or maximum or an absolute minimum or maximum? We okay? Yes, ma'am.
Would the 0, 1, would that not be a local minimum either if there's nothing going on?
Very good. I'm glad you asked that. You're correct. 0, 1 would not be a local minimum because I don't have the other side to compare. Right? I would need to really know that I'm in the bottom of a valley. I would need to be able to look left and right to be able to tell that I'm at the very bottom, and I can't. So you're exactly correct. That would not be a relative minimum, only an absolute. Yeah, good. Is 5, 5 anything? No. Poor little 5, 5. It probably wants to be something, right? But it's not. It's not. It's not an absolute max because the other one's bigger, and it's not a relative max because I don't know what's going on the right side of it. So poor little thing, it's not. So extreme value theorem, this is something, another calculus thingy, extreme value theorem. Basically all this says is that if a function is continuous on a closed interval, that it will have an absolute max and an absolute min. That's all. That's all it's saying. If a function is continuous on the closed interval, then the function will have an absolute max and absolute min. What that means on the other side of it is if the function is not continuous on a closed interval, that means that it doesn't have to have an absolute max or absolute min. It might, but it doesn't have to. This theorem is a have to. This has to. But if this isn't true, then it doesn't have to. It might, but it doesn't have to. Does that make sense? Okay. All right. Now let's do a few examples. So first, we're going to do some examples on even, odd, and neither. You could graph it and look at it if you wanted to. What we're going to do, though, is we're going to do this algebraically to determine whether they're even, odd, or neither. So the algebraic test, I'm going to find f of negative x. And so that would be, I plug in a negative x where the x is, and then I simplify it. Let's see, negative x times negative x is x squared. And then I have minus x. And so now what I'm going to do is I'm going to compare. I compare this original function with the new one, with the f of negative x. If they're identical, then it's even. If they're exactly opposite, then it's odd. And if it's a mixture, it's neither. So as we look at this, we see that the x squared is still x squared. That's the same. But the x is now a negative x. That's not the same. So this is a mixture, which means this one is neither. It's not exactly the same, and it's not exactly different. It's a mix. Okay, so that means neither. It's neither of them. On part B, I would prefer to write this without negative exponents before I jump into figuring it out. So I'm going to rewrite this without negative exponents. I would encourage you to do the same. It's really hard to get a feel for what things are when they have negative exponents. It's very difficult. So I would recommend that you change it. All right, so now let's do our test. So f of negative x is 1 over negative x squared, which simplified. Okay, so I turned out that with the same thing I started with. We're exactly the same. That means this one is even. Okay, how are we doing on even and odd? Is everybody okay? Okay. All right. On number 2, we're going to do several things. We're going to look at intervals of increase, decrease, relative extrema, and absolute extrema. Just the last thing that we were talking about. So let's work on that. So part A, we're looking at increase and decrease. Okay, so here we go. So when we were talking about increase, decrease up here, we were looking at a whole interval. So here we decreased from -6 to -4. Okay, that's what that pink part means. It was like an interval, right? We're looking at an interval. We're not looking for just one value. Okay, so let's look at increase. So increase looks like from here to here, this is increasing. So what is that? That's from -8 to -2. Now, students usually are like, it's kind of weird that we're writing down x values about increasing and decreasing instead of y values. What that's doing is it's setting up an interval on which the graph is increasing. It's an x interval. Okay, the x interval is where the graph is increasing. So let's look for some more increasing. It looks like from here, 0 to 2, we're also increasing. And then we got one more increasing part right here. It looks like from 5 to 7, we're increasing. Now let me talk about the parentheses versus brackets. For increase, decrease, there are some textbooks that use parentheses and some textbooks that use brackets. And you're thinking, what? Mathematicians disagree about something? Yes, we actually do. This is like a hotly contested. You're like, oh my gosh, why is that hotly contested? Or what's the big deal? Parentheses or brackets? It is, and mathematicians have reasons for both ways. So I'm not going to get into the nuances here. I just want you to know that when we're talking increase, decrease, you could use either. You could use parentheses or brackets. I'm going to use parentheses because it doesn't make any sense to me that if you're at the top of the mountain, you're still increasing. So I'm not going to include it, but people do, and it's okay. Okay, but I'm not going to. So I guess that shows you which camp I'm in, doesn't it? Oh well, it's okay. Let's look at decreasing. Okay, so we decrease this right along here is decreasing. So we're decreasing from -10 to -8. Let's see, we got some decreasing going on here. That decreases from -2 to 0. And then right here is my last part of decreasing. That's from 2 to 5. All right, that's our increase, decrease. Now let's look for relative extrema. Relative, so we know we need to be at the bottom of a valley or the top of a hill, not at the end points. Okay, so let's look for relative minimums. So I'm actually going to write the whole point. So I'm going to say f of -8 equals -4 because if I remember right, that's what your homework does. Your homework makes you write the whole point. So let's just go ahead and practice that. We're writing the whole point. The actual relative minimum value is -4, but your textbook wants you to write the whole point, so let's write the whole point. We have another relative minimum here. That's the bottom of a valley. So that's f of 0 equals 0. And one more relative minimum right here. Again, that's the bottom of a valley. So f of 5 equals 0. So we're writing the points instead of just the actual minimum value. Okay. Let's look at our relative maximums. Okay, we're looking at the top of a hill. We want to be at the top of the hill. So this right here, -2, 6, that's at the top of the hill. And again, we're going to write the point out. F of -2 equals 6. Looks like we have one more right here, top of the hill, 210. So f of 2 equals 10. And those are our relative maximum points. Okay, are we all comfortable with the reasoning why -10, 0, and 7, 3 are not relative maximum points? Are we all okay with that? They're not, because I don't know what's happening on the other side of them. To be relative extrema, I have to know what's happening on the other side. So those poor little guys are just out. All right, so now absolute. Now we're going with, remember, absolute is just the very biggest. So we want the absolute max and the absolute min. Okay, so we look over the whole graph. We want the very biggest y value. The very biggest y value is 10. So I'm going to write f of, because they want the whole point, like I was saying, your book is wanting the whole point. F of 2 equals 10. Okay, that's the very tallest, the very biggest y value. Now we want the very smallest y value, which would be -4. So f of -8 equals -4. Okay. How we doing? Everybody okay? Yes? Okay. Let's move to our, let's see, does everybody have what they need here? Yes? Okay. Let's move to average rate of change. We're going to do a couple of different problems on average rate of change. One of them is looking at the average rate of change off of a graph, and the other is with a function. I mean, written out like this. We're just doing a couple of different things. So this point right here would be like our A point. A point is the smaller point. In other words, the one farther left on the axis. This would be like our B point. Okay. So A, in this case, is negative 1, and B, 1, 2, 3, 4, 5, B is 5. Okay. Great. My formula is for average rate of change, which is a calculus thing. You're learning calculus right now. F of B minus F of A over B minus A. Okay, that's the formula. So if A is 1, we need to look at here. F of A is 0, right? The Y value is 0. And if B is 5, F of B, see that Y value is 1, 2, 3, 4. So now that we know those numbers, we're just going to sub it into the formula. So it's going to be 4 minus 0 over 5 minus a negative 1. Now I'm going to put a little note out here. For my students that like to conserve energy, and I might not have any students in here that like to conserve energy. And you know what I'm saying, okay? Some students want to skip this thing. You cannot skip that. You have to. So this is a note. Note, yes. You have to write it in the formula. You have to write the numbers in the formula. Why? Because I'm already training you for calculus. That gives you a point, plugging in the values in a formula. You can't just jump to an answer. It's not a thing. So yes, you do have to do that step. Now you can write your answer. I mean, you can do the rest in your head, but you have to show that you're using the formula. So we've got 4 over 5 minus 6, so 2/3. So our average rate of change on number 3 is 2/3. Okay, how we doing? All right, last one. We're going to do same formula. Average rate of change is a formula. F of B minus F of A over B minus A. Okay, in this scenario, A is this is A, and this is B. Okay, A is always the smaller one, and B is always the bigger one. When it's abstract like that, we're just going with A is 1 and B is 1 plus H. We don't know what H is. So I know what to put in the denominator, but I need to do F of B. So I'm actually going to do that inside the formula. I hope that's okay with you. So this is my function. So I have 4 minus, now I'm going to open up that hole and I'm going to put in B, which is 1 plus H squared. This should be kind of familiar to you. This should seem like kind of what we did yesterday with our difference quotient. Remember that? Kind of. It's not exactly, but it's kind of like the difference quotient. So now I'm going to open up, I'm going to write my function again, and I'm going to open up that X spot, and I'm going to put in the A, which is 1. And that's all over B, which is 1 plus H, minus A, which is 1. So I want to pause here for just a second and make sure we're all okay. Yes, ma'am?
Why did you use the brackets?
Because this negative right here, and that's a good question, this negative has to be distributed to everything that F of A creates, everything. And so if I forget, and this is my issue, if I forget to put a bracket, sometimes I forget to distribute the negative. And so that's why I do that. I don't want to forget to distribute the negative, because I've done that before. Has anyone in here done that before? Forget to distribute the negative? We all have, right? I bet there's nobody in here who hasn't forgotten that. So I try to make it safer for myself so that I don't forget. So that's why I got the brackets there. Okay. Is everybody okay with plugging in? All right, so let's keep going. So now we just need to simplify. So I have 4 minus, and I'm going to have to put brackets here because I'm going to probably forget to distribute the negative if I don't. So we'll go out here. I'll just do some scratch work. 1 plus h, 1 plus h. If you're not able to do that in your head yet, you should like go to the side and do some scratch work. So that gives me 1 times 1 is 1, and then plus h plus 2h plus h squared. Okay, so that's what's going to go in that spot. 1 plus 2h plus h squared minus 4 minus 1 is, what is that, 3? Okay, all over. Combining like terms in the denominator leaves me with an h. Okay, we're getting close. We're almost there. Algebra, more algebra, yay. All right, let's distribute the negative. So I have 4 minus 1 minus 2h minus h squared minus 3 all over h. And so combining like terms, let's see, what do we got? We got the 4 minus 1 minus 3. Those all go away, don't they? Because that's 4 minus 4, which is gone. So then we have negative 2h minus h squared over h. Oh, this should be very reminiscent of yesterday or the day before. Any way I can simplify that? Yep, absolutely. Yes, ma'am. We're going to take out an h in the numerator. That leaves me negative 2 minus h. So I get to get rid of the h's. Yay. And my final answer is negative 2 minus h. All right.